start streaming. Okay. So, what we've done so far is we had. Why did I lose this? We've had 3 different, like, free body diagrams, kinetic diagrams. Those have all been the same kinetic diagrams with different forces acting on these things. And the last step for this case problem is comparing and contrasting. So what's the difference? Why was it important? Is there something that you would do differently? It's the wrapping up section of this. So first question, do we know where to go from here? We have differential equations, we have solutions to differential equations. Do you know yes what you're doing now or no? Not sure where to go. Some yeses? Any no's? No's? It's okay. Some no's? Okay. No's are fine. No's and some maybes. Okay. All right, so main kind of like deliverables. We've done a lot of the heavy lifting together, and I'm doing that on purpose so that you're not like at home just struggling with differential equations, like, oh, I don't even remember this class, or I haven't even gotten to this yet. So the meat and potatoes of this is, what are the free body diagrams? What are the kinetic diagrams? Like, what are the forces that you're considering, and why? Like, and that's introducing the problem. So you can show them, you can describe like where they're coming from. So that's first part. Next is your ODEs and solutions. This is like the methods of, you identified a problem. So part 2 is, here's how I solved the problem. It was a differential equation. Here's an answer to these 3 different differential equations. And then this is our last part, is 3. Wrap up. Making some kind of statement of like, why did I go through this? Which is like, one way of engineering is just, you never model anything and you just build the damn thing. And it works. Like, that's how we got internal combustion engines. Nobody was doing thermodynamics before we built gas engines. But then afterwards, we started optimizing it, and the only way to really optimize it is start doing some thermal work. So that's what we're doing here. Is like, we're doing some work, we have variables that we can control and kind of optimize. So now we can compare and contrast, either choosing, or we can say like, it should be some combination of different methods for the best result. So that's this last step. So one great way of comparing and contrasting is like, you show 3 curves from the 3 different methods, and then talk about like why one is either better or worse, or even just like comparing, like what's the difference between the 3. Why does one stop, the other one keeps going? What do we think? A little better? So what do you want to compare? This is a chance to, like, you can either try it and I could try to troubleshoot, or we could just do it. You can ask, like, how do I do this? What do we want to do? Yeah.
You want to maybe compare the impulse between the three systems delivered to the object?
Yeah. So what would we need for, like, impulse if we were comparing those?
Delta T?
A delta T? Yeah. Yep. So we'd need some kind of, like, force in time, right? Force times time. We can also use, we need, like, delta T. We can also use, like, the change in MV and how long it took. So really, if we had, like, MV, if we looked at that delta MV, that is our impulse, right? Am I? What do you think? Agree or disagree? Is there a different impulse from these three different methods? Yeah. Let's try it out. What are the three different impulses that we experienced here for A, B, and C? What do you think? But impulse is both, like, force and time. Oh, for that. But at some point it comes to zero, right? So the velocity was 3. At some point it's 0. So the total impulse has to be 3 minus 0. Is there different impulse values?
Is the free fall the same convention?
What's the fundamental for X is greater than
Okay, I think it's different, but how different? Okay, you think so?
Oh, right. X is let's see if you can big line. The spread still is very messed up. So if I want to stop,
Did anyone find like an impulse value? Is it different between these? What do we think for now? Who says there's no way all three of them all have different total impulses applied? Yeah, we can do like thumbs up. Definitely different.
We were confused because like in the second one, it never actually comes to a complete stop.
Yeah.
So
Okay.
how do we find our delta V? We don't know what it is.
Delta V is the change in velocity, right?
If it never goes to zero, what is the change in velocity?
Well, the velocity goes to a constant value. It's let's see. Let's find our velocities, right? Oh wait, yeah, I think this is right. So now if I look at like what is velocity versus time, so the spring we kind of already said, like it's gonna keep moving, but total impulse that gets applied was initially it was 3, it goes to 0, and then keeps accelerating, so it changes. But biggest impulse applied is going to be that 3 minus 0. For our for the damped one, it goes from 3 down to, we can calculate it, but it looks like 0.1 or something. It starts moving really slow because it's moving through some viscous fluid like that. So there, definitely we have a different delta V, right? all three methods have the same impulse. I mean, one of them is slightly different because it doesn't actually stop it. Like it slows down, but it doesn't bring it to a stop as it's moving through that fluid. But total impulse is that change in momentum. So that's a nice like comparison between the three. Like they're all similar. Two of them are exactly the same. Like spring and friction, total impulse applied has to be the same if it brings it to a stop. And then for that fluid, it's got to have enough to slow it down to that constant value. Now one we could figure out, right? Because we know the so roughly 0.2. So I was off by a little bit. 0.2, something like that. 0.1 something. 19. Yeah, 0.19. Go 0.2. So it's similar, right? Impulse is similar. Yeah.
Because if you want to, say, combine two systems, could you really just take the two equation motions that we created and just put them into one equation together, or would we have to divide it into one?
Yeah, like, so if you want to,
If you want to combine water and spring, could you just add velocity decrease of water to the decrease in spring?
yeah, do they add up? They do, it's a process of convolution rather than like direct adding. So it's still linear system for spring and damper, but it ends up like there's an e to the negative t times that sine cosine value. So it changes it a little bit, but a little different. Yeah, if we wanted to say that there's both force of a spring and force of that damper, we would have this new differential equation. This one's getting into like vibrations analysis, which is a whole nother class. But there are, like, you could look up solutions to this differential equation too. If you're like really like, I gotta know, like I gotta be able to combine them and I want to see what the answer is. That's normally how these systems are designed, is you add springs and dampers so you can tune both of them, make it stiffer, less stiff. It's called that spring mass damper system. all right, I'm gonna check in, see where people are at, and yeah, if we want to try something else, I'm happy to like share, like do code, share code, or any other kind of method next. More physics, more engineering.
That's like your domain, right? It goes between 0
Yes. I distribute where it wants spaces. It just creates X amount of units between your first number and your second.
In total.
What number did you say? Yeah, I know what.
What number is it for V and triple I? In Roman numerals, what is V triple I? 8. Okay, Jonathan 836 as mascot in the middle, in the mid-1990s, who still thought his color was Kill. And Kill.
So we didn't skip one, we just had him for like a minute.
Oh, so basically his color got caught in like a head. Very similar.
Oh yeah, that guy, yeah.
Okay, so it's not the line spaces.
That's what we're trying to do.
Also, I just realized, that's also given the wrong
This?
Yeah, it should be at 0.05. Or sorry, about point. Which is actually right. It's not another.
Yeah.
Watching the What? It's not what we see.
Yeah, and it's only within the.
I asked what because I heard.
Oh, wait a minute. This?
This. She wants us to do this. This is just
No, I don't.
Yeah, lots of comparisons are especially nice. The problem is the spring one is so nonsense. So spring one's very good. Why is this spring? That's
So one thing that nobody really asked for, but I'm going to tell you anyway, since we're trying to compare and contrast methods, use the same figure to plot. Like if you're trying to plot position, plot it all on the same figure. So right now I have like that, the damped motion and the spring motion. I could add the friction motion too. What value of acceleration did we have for our friction? How much acceleration did we want?
My equation is solved for infinite energy.
Infinite energy? Yeah? Yeah, if you get infinite energy, I mean,
My spring equation, for whatever reason, goes up in velocity.
oh, the velocity
It
increases?
goes from 3.1 to 4.11 and then sets off.
Oh, it shouldn't do that. I don't know why. That's probably numerical uncertainty. All right, no takers on defining acceleration for friction. How about 3? 3 meters per second squared. What would that give us? How long would it take to stop? If we have 3 meters per second squared, our initial velocity is 3 meters per second. How long does it take to stop? 1 second? All right, try it. Oh, I should plot it, right? So sure enough, in 1 second, if I have 3 meter per second squared of acceleration from friction, it does stop it. It brings it to a stop after 1 second. But how far did I go? One and a half, yeah, a little over 1.5 meters, so like 4 to 5 feet, something like that. Compare that to like even the spring looks like it stopped. Even though the spring is bouncing, it looks like it stopped compared to that friction. Same thing with our damper. Like that thing basically looks like it stopped compared to the motion that we have at 3 meters per second squared. This is one of the reasons why it's good to plot everything together so you actually have a comparison. You can see what the difference is from one method to the other. So maybe that's too far. Like I don't want it to move 5 feet. I want it to move a lot. Stop much quicker. So I could use the spring as an example of like, all right, the spring brings it to a stop at like 0.1 or 0.7 second, 0.07 seconds, like less than 0.1. So let's make it 30. Like 10 times bigger, it'll stop 10 times faster. Now I have this graph. Is that right? What's wrong here? Or what's right? I don't know. Maybe that's exactly what we would expect from brakes. When you hit the brakes, you go flying backwards.
No?
Not really, right?
This is saying to the last year of the decade. Come on, you just because it's what you showed answer this question.
So what's wrong with my like solution, my kinematic like? All I did was plug in this kinematic equation. Why is it not giving me what I want? Is it negative? No, it's not stupid. Why is it not giving me what I want?
It's got a
Something's weird, right? What's weird? What's
No. Back to crash.
All right, so the graph that I have right now says that at 1 second, my block will be 12 meters high. It'll be 12 meters above where it started due to friction. Where am I going wrong? Something's got to be wrong, right? Something's wrong. What's wrong?
It doesn't stop when velocity hits zero.
Yeah, so something's got to change when velocity hits zero, right? What changes when velocity is zero for friction? Acceleration goes to zero. Like friction is only happening when you're moving. As friction brings you to a stop, the force of friction is no longer acting. So acceleration is negative 30 for v more than 0, and a equals 0 for v equals 0. So as it comes to a stop, there shouldn't be an acceleration. So if I'm going to do that, like since I did it in Python, I could solve for at what time does velocity equal 0, and then plug in, say, the acceleration 0 at that point. I'm not going to do that. I'm just going to say, give me the maximum value. And then everything from that max value to the end of this is the max. How does that look? A little better? That's more like what I would expect from like falling into something that's clamping it, right? Where maybe it doesn't stop instantly, but it slows down and then comes to a rest. So as far as like wrapping, so if the goal is like compare positions as a function of time, this would be the graph that I'm comparing. If you want to talk about like velocities and time and impulse, maybe it would make more sense to look at velocity graphs, like velocity versus time. But at least here, I've got 3 positions versus time. It helps to label them, right? And label the axes. Any initial thoughts on like things that are the same, things that are different? I'm just trying to help write your wrapping up section by asking these questions. Like, what's the same? What's different? Let's compare, contrast, wrap it up. Yeah.
Would you be able to color coordinates?
Yeah.
Really quickly.
this is where the derivative notation is so that the velocity increases before it decreases.
Yeah.
The rough surface. I also changed like the velocity,
Kinda like
so
that.
thing goes up.
For C.
For C.
Somehow, that's what? Well, this is your first line, and then
I swear it in the. Because it started off at approximately 0.
Just make your
Are you using the position graph?
No, I'm telling you.
You feel like you're not
So V0 actually is that where that is 0. Oh, the peak. Oh, I understand. Velocity T. Like the string makes sense.
Like mine is zero.
It's like
I would guess it's something like how Desmond's guesses.
assuming that it's let's get rid of the boundaries. And that's still centered 0, 0. And that's still possible. But then there's nothing for it. There's no extra value for it to scale on a translate by.
Oh, yeah, because there's a little C. So you're going through the wing
Expansion. And we're supposed to do like a little bit of discussion, right? Oh, this one's then put down the temperatures. It smells like Thai guy. It doesn't smell good when you get it home. You just have a lot of time. Actually, you know, logs usually that sound. Yes, especially when it gets cold and you have to already cut the wood to length.
Sure. What if you keep them inside the shed?
Do you have a big enough shed to fit a log piles?
Yeah.
Because now I'm sitting more than one degrees over. Still pretty much front row.
Yeah,
I think we're on the front right. Oh, you're on the right. That works.
thanks. You too. Have a good weekend. Thank you.
Another position tracking site?
Okay. You like tennis?
I just didn't want to go.
No. You're
So
still coding. You're just doing it.
beforehand, so that's right. I kind of do the point one which is good. But then when I graph the derivatives, it does start at the point one it's supposed to. But it will go up with the word. So it's very as well.
You're doing DDS.
Yeah.
Oh, I see. Because it's X.
I originally, actually, as originally I wrote the entire equation, then maybe I wrote the equation wrong, and then I used derivatives instead, but it's maybe the exact same graph.
Why is this one X more than equal to 0? There.
Just so that it's not negative. X is not changed.
Oh, I
So
see.
that's just the domain of the entire equation.
Okay.
So, Mark, I actually think I can fix this up with this like a calculation problem, but would this be okay to submit, even though it's slightly weird looking? Or
Yeah, why is it so? I don't think. Are these constants, right?
Yep. M is set to 0.1, G is set to 9.81, and every time I was like, what if K was weird, so I substitute K for 100.
No, like the 3.1.
3.1 is the initial velocity. That's the initial velocity over W.
Mm-hmm.
That is just good.
And then this one. Is that, are those, like, are these definitely
These are
constants?
Yes.
That are correct.
I mean, it matches the equation we created on board, so I hope so. It should just go straight down. I can't think of a reason why something falling with speed up or down.
No.
I have a question. So for the case study, we're literally just getting like a picture of a graph, like on like decimals or something. Like I'm